Welcome to the NimbleSig III RF Analyzer demonstration video. We have put this video together to try and demonstrate some of the features of the NimbleSig III RF Analyzer. This RF Analyzer consists of a dual output RF signal generator that can be operated over the frequency range of 200 kilohertz to 200 megahertz. Either generator can be operated independently on separate frequencies, or they can be operated on the same frequency with a specific phase offset. At the moment, RF generator A has been set to 200 megahertz. It's connected to a frequency counter. I can change the generator frequency quite simply by pressing the frequency button. I'll change it to 50 megahertz. So I've entered 50. I'll press the megahertz key. It goes to 50.00 megahertz. The analyzer has a front panel that where the various modules inside are cabled out to the front panel so that they can be patched in for doing RF network tests as required. It's got capabilities to match levels, to shift frequency, measure relative phase and gain. It will just do a wide range of RF measurements. The NimbleSig III RF Analyzer has been designed for development purposes for easy access to the various modules inside. For example, to access the RX62 RDK controller from Renesas, it is just a matter of opening the front panel lid. It hinges back, and there you see the RX62N RDK board with the future electronics companion board plugged into it. And on top we see the underside of the Reach Technology intelligent SLCD display. You'll note that the ribbon cable that feeds the modules in the RF box, which forms the base of this unit, is plugged into the edge of the companion board and passes through the rear apron. This segment of this video will demonstrate the graphics user interface entry associated with the NimbleSig III RF Analyzer. We'll start by demonstrating how to change the frequency of one of the generators. We'll change generator A to 5 megahertz. As shown, generator A is currently running on 12 megahertz. To change it, we would press the frequency key. We're going to change it to 5 megahertz, so we'll press the 5, and then we'll press megahertz. And you'll see the frequency display is updated to 5 megahertz. And it does that as a result of a reply received back from the generator module confirming that the frequency change has taken place. To demonstrate again, this time we'll use the kilohertz entry, and we'll change the frequency to 10.7 megahertz, which is the IF frequency. To do that, I'll press the frequency key. You'll notice that I get an FA text above the keyboard here. This is called the user entry text, and what it shows is the command syntax that will be sent to the generator module. It starts out with an FA indicating there's a frequency A command. We were going to change it to 10.7 megahertz, so I'm going to put in 10700, and that's in kilohertz. Press the kilohertz key, and you'll see that we now have 10.7 megahertz displayed. Similarly, we can change the frequency of generator B. I'll just quickly do that. We'll put generator B on 5 megahertz. Pressing the frequency key on the B side, we get an FB command this time. We'll set it to 5 megahertz. Just pressing 5 and the megahertz key, and it pops up on 5 megahertz. We can also set both generators on the same frequency. That's exactly the same frequency with a specific phase offset. To do that, we press the frequency key on side A, and then the frequency key on side B, and then enter the frequency we want. We'll just put it on 1 megahertz in this case, and we put it on 1 megahertz. You see both generators are running on 1 megahertz now, and also you'll notice that the phase offsets shown for both generators. Generator A is 45 degrees and generator B is 90 degrees. This demonstration is intended to show some of the versatility. At the moment I've got it connected up with the output of generator B feeding the local oscillator input of the mixer. I've got generator A feeding feeding the input of the RF amplifier, and I have the output of the RF amplifier feeding the signal input to the mixer. I've connected the output of the mixer to feed the 10.7 megahertz IF detector. At the moment I have generator B set to 110.7 megahertz, and the intent here is to use that as the local oscillator. And we've got the signal from generator A set at 80 megahertz, so the difference frequency between the two is about 30 megahertz. It's well away from the IF frequency, so we don't expect to get much signal through the IF filters at the moment. So the first test will be, the first demonstration will be to demonstrate the selectivity of the IF filtering. So we'll switch over to the menu and select the IF detector display, and I should mention that I've got the variable gain amplifier set to 0 dB at the moment, and so it's really got close to zero insertion loss. And similarly, I've set the amplifier in the IF detector to 0. The power output of the detector is running at the noise floor there at the moment at about minus 77 dBm, which is a typical noise floor for it. And to prove that, I'll just disconnect the input to the IF, and there it's disconnected now, and it's sort of settled down a bit, but still around minus 77. And hook it back up. You can see a little bit of additional noise from the mixer and the IF amplifier and the generator output all combined. Anyway, it's almost as if there's no input signal at all at the moment. So now I will exit and go back to the RF generator menu, and we'll set the frequency now to 100 megahertz, and press the megahertz button, and now the difference frequency will be 10.7 megahertz, the center of the IF. So we expect when we go back there to see more signal than we had before. So we're going back to the IF detector, and there we have it. The signal has gone up by to minus 15 dBm. So it would suggest a net loss after going through the variable gain amplifier and the mixer, and with the frequency shift from 100 megahertz down to 10.7 megahertz, there's been about 5 dB of loss. If we wanted more sensitivity here, I could increase the gain of this detector. We could switch it over to the high gain range, for example, and we've thrown in 16 dB, almost 17 dB of gain in the detector, bringing the output level up to power level up to about 2 dBm. The limit is about I don't know if it'll reach plus 20 dBm, but the power detector limit is about plus 10. So we could increase the gain and sort of bring it up to the limit. We'll just see what we can get out of it. Well, we actually managed to get a 20 dB indication, but it'll be in the compression portion of the out of the linear portion of the power detector. So it's probably not a very accurate reading up there. But as you can see, we can get quite a hefty output level into the detector. Now I don't imagine we can drive it that hard with I'm going to try and set it back down to about 0 dB gain here. I don't think we can drive the output of the mixer that high to get it back up to that level, but we'll just see what we can do by increasing the gain of the RF amplifier and driving the mixer harder. So we're sitting at a level of -15, so we'll try and add 25 dB of gain to that, which would bring it up to about a +10, I guess. So we'll go over to the variable gain amplifier. We see the gain indication at 0.5. We're in the low range. I don't know if we can get 25 dB more out of it or not without going to high range. High range, by the way, switches in a preamplifier in the amplifier, and so we had to go to high range. We'll get it down to about 25, do a fine adjustment, then we'll go back to the menu and go back to the IF detector and see what happened. And we thought we might get up to +10, and it seems that we got up to +9.4. I imagine we're driving the mixer pretty hard right now, and it's probably a near saturation. I'm doing all this to demonstrate the flexibility of this instrument, because what we've done here is we've taken a 100 megahertz signal, put some gain in front of it, and shifted it to 10.7 megahertz, and then put it into a narrowband detector to detect the signal strength, and with the adjustable gains in 2 different areas. And with all this versatility, the NimbleSig III RF Analyzer can be adapted to many test environments to match up the levels and to make measurements on external devices under test. And with that, that's the end of this demonstration. Thank you very much.